Dear students, so in the last video lecture we got introduced to the application of consistent deformation method in analyzing indeterminate structures. So the structure what we dealt in the last video was a propped cantilever. Now we are going to think about a different case of consistent deformation approach. So this is the basic problem definition. So we have a continuous beam. Okay. So if one end happens to be a cantilever, then we can think of the prop cantilever option. So what we are having now is a continuous beam. So let there be some kind of loading. Let there be I'm defining some points here. Let this be A, this be B, C and D, and I'm considering some kind of loading. Say this be a UDL 2 kilonewton per meter, and let there be a moment at this point, okay, having magnitude 10 kilonewton meter. Fine, and it is acting clockwise. And let the distance be this be 1 meter, 1 meter and 4 meter. And let the first segment have the flexural rigidity as EI, and the second segment let it be 2EI. So we are just including almost all the complexities that is possible. But I'm not going to tell that this is the worst case, but this is a complex case. So here we want to analyze this. So I hope you remember the steps. The first thing, you need to convert it into a beam of forces. So there's a hinge. I'm ignoring the horizontal component because there is no horizontal forces in the system, so horizontal reaction is going to be zero. So I'm just ignoring it in the very first step itself. Now I have three rollers are going to give me one reaction. Hinge is going to have a vertical and horizontal reaction, but the horizontal reaction is zero. So on this we are having this kind of loading, okay, 10 kilonewton meter and 2 kilonewton per meter. And I'm giving some names. So this is RA, RC and RD. So what about the DS value? DS is equal to unknowns minus equations of equilibrium. How many unknowns are there? There are 3 unknowns. How many equations of equilibrium? I will write 2. Why is it 2? Because sigma fx is not valid anymore because I neglected the horizontal component, so sigma fx is no more available. So what I have is the ds value as 1. So that's the very first step. Now what is the second step? In the second step we need to identify which type of primary structure or the basic structure we are going to adopt. So I told you there are 2 options for us. One is to choose a cantilever, the second one is to choose a simply supported beam. So once we analyze the structure given in the figure, if I'm removing this support, what I'm going to get is a simply supported beam. So I can choose the simply supported beam as my basic structure and consider this support reaction as the redundant. Okay, once I release this, it becomes a determinate structure, hence this is the redundant. So in this case, RC is our redundant. Now, what is the next step? In the next step, we'll be plotting the subfigures. And what decides the subfigures? The ds value. If ds equal to 1, I require ds plus 1 subplots. So ds is 1, so I need 2 subplots. So simply plot 2 simply supported beams. Okay, when I add these two, I should get this. So all these things need to be considered here. Fine. Now, as I plot this, so I have this reactions I have already considered here. Now what I am left with is the loads. So what is the loading for the first subplot? The first subplot should be loaded with whatever external load is there in the problem. So here the external load is one is this 10 kilonewton meter, other one is the UDL. Okay, so that's the loading for the first subplot. And for what for the second? The redundant, which means RC. So this is 2 meter, this is 4 meter. Here I have 1 meter, 1 meter and 4 meter, and we should be very careful because the flexural rigidities are different. So for this portion it is EI, EI and 2EI. Here it is EI and 2EI. Okay, because that's a very common point where we make mistake. While we are substituting the equations, we may tend to forget this EI and 2EI difference. So I have the subplots. Now it's the time for us to assume the displaced profile. So how this will be displacing? So this part you can easily predict. This is a load acted upon, and these two are like supports. So you are having something like this, and there is one support, I apply a load, it will bend something like this. So this part is comparatively easy to assume. What about this side? When I apply a moment like this, a clockwise moment, okay, what it does is it lifts the left hand side and pushes down the right hand side. So the profile what I may get here is this part may go up and it may go down and it may go up like this. Okay, so this is a complicated profile for prediction, but you don't have to worry about it. I will tell you why. So now what about this? How will this deflect? This will be deflecting like this, right? This will push it down. This will take this portion up and the other portion down. So I'm going to get a shape like this. Here the profile is going to be something like this. And now it's time for me to think about the compatibility equation. So what is the compatibility equation? The compatibility equation are always written considering the redundant. So here the redundant is the reaction RC. And you can find here RC is a vertical reaction. The displacement caused by a vertical reaction is vertical deflection. Displacement caused by a moment is rotation. So this is a vertical deflection. So I will be dealing with the parameter YC. Okay, because RC is my redundant, so YC is the parameter what I'm going to think about. Now, what is the YC in the original structure? C is a roller, which means that it won't allow vertical deflection. So in the original structure, YC is 0. What about the substructures? At the point C, I'm having some deflection here. Here also I'm having some deflection. This is the first subplot, so YB1, second subplot YB2. So I'm having my compatibility equation YB1 plus YB2 should give me, sorry, I wrote it as B, it's not B, it is C. Okay, this value should be C, YC1 and YC2. Okay, YC1 plus YC2 should be equal to YC, which is equal to 0. So that's what my compatibility equation is. So I have that. Now I can just apply the unit load method to calculate the different parameters YC1, YC2 and apply this, get the solution. So now I'm going for the unit load part. So when I go for the unit load part, I require a capital M figure and a small m figure. Okay, that's what unit load method basics are. So what should be the capital M figure? I have mentioned it in the last video. The capital M figures are these figures itself. So these are my capital M figures. What about the small m figures? In the small m figures, we'll be applying unit load at the location where we want the displacement. So here the unit load figure is going to look something like this. These are the two figures what I have. I need deflection at C, right? This point is C. I need deflection at C, which means that I need to apply a unit load, which is basically a unit force because I'm talking about vertical deflection at the point C, which is 2 meter from here and 4 meter. And what about here? Here also I want deflection at C, so I'll be applying 1 kilonewton. Okay, so these are my unit load figures. Now it's a matter of calculation. So we'll construct the table. Okay, S, then E, L, O, M, M. Now, how many segments are needed? That's a point where we need to focus a bit more compared to the earlier problems. Here, if you are observing this, we need 2 segments. Okay, 3-point forces, 2 segment. But in the capital M figure, you can see there's 1 point here, 1 point here, and this is the location of another point load. So I may think about how many segments are required. Segments are basically considered by considering in a portion, if the expression for bending moment remains same, that can be considered as a segment. So when you look here, say if I'm taking a section here, okay, now on the left side I will be getting an expression for M where there will be just one reaction, okay. But if I'm considering a section here, there are two reactions, so these should be separated. Here I should have one section, here I should have one section, so this is segment 1, this is segment 2. Now when I take a section here, what happens? If I'm looking to the left side, apart from these two, there is this UDL also, so this should be a separate segment, okay. Throughout this section, the expression for bending moment remains same, so I need to have 3 sections, one here, and one here. So this should be divided into 3 segments, okay. So segment 1, segment 2, and segment 3. So that's how this is getting divided. In the similar way, this also should be divided. That's a concept from unit load method. Whatever divisions you're having for one figure should be the same for the division for the next figure, okay. So in case of calculation of YC1, this is the segment division. Now we are going to this part, YC2 calculation. So how many segments are needed here? If I take a section here, 1 force. If I take a section anywhere here, I am having on the right side just 1 force. So just 2 segments are enough. 3-point loads and 2 segments. So let this be segment 1. Okay, and let this be segment 2. So there is no compulsion that you should have the same segments for YC1 calculation, that is substructure 1 and substructure 2. You can have different segment divisions, no problem at all, okay. Now, so this is the figure 1, so I'm calling this as RA1 and this as RD1, the reactions. So figure 2, so this is RA2 and RD2. And I have told you earlier, when we are dealing with simply supported beam, there is an additional step that comes in between the figures and this table. That is the calculation of these values. Okay, we need these values because only if we have those values, we can write the expression for bending moment. So the next step is calculation of RA1 and RD1, RA2 and RD2. Okay, so let's do that. So I want the value of RA1. So I'm taking moment with respect to RD1 in this figure. So what will be the value? Say if I'm taking sigma MD1 equal to 0, what will be the expression? RA1 times this distance, and it is going to rotate clockwise. So RA1 times 6 meter clockwise, so positive. Then there is this 10 kilonewton meter clockwise, so plus 10. Then the effect of this is 2 is the magnitude for 4 meter, so 2 times 4, that is the magnitude is 2 times 4. What about the lever arm? I'm taking this as the point, so lever arm is half of it, which is at a distance of 2 meter, so times 2. And is it positive or negative? So here the load is like this, so it is anti-clockwise, which means minus equal to 0. So from this I will get RA1 is equal to, okay, so 2 times 4 times 2 minus 10 divided by 6. What I'm going to get is RA1 as 1 kilonewton. Okay, 8 to 16, 16 minus 10 divided by 6, 1. Okay, I got RA1. What about RD1? So I can use sigma Fy equal to 0, and I'm taking this as the positive sign convention, so upward positive. So RA1 plus RD1 equal to the downward, which is 2 times 4, which implies RD1 is equal to 8 minus 1, that is 7 kilonewton. So I have the values of RA1 and RD1. Now I'm going to calculate RA2 and RD2. Okay, so what will be RA2 and RD2? So I'm going to take moment with respect to D2. Sigma MD2 equal to 0. What will I get? RA2 multiplied by 6. Okay, clockwise. Then RC times 4, that is also clockwise, plus RC times 4 equal to 0, which implies RA2 is equal to, okay, what will be the value? 4RC by 6, that is 2 by 3 RC, and that is negative. Now sigma Fy equal to 0, on this I will get, I'm taking the same sign convention, RA2 plus RD2 plus RC equal to 0, which implies RD2 equal to, okay, RC, what is the value of RA2? RA2 is minus 2 by 3 RC. This is RC. So when I take to the right, what I'm going to get is 2 by 3 RC minus RC. So it is basically 2/3 minus 1. Okay, what I'm going to get? 2/3 minus 1, it is minus RC by 3. Okay, minus RC by 3. So I have the value of RA2 and RD2, RA1 and RD1. And what about here? Okay, in the unit load figure, what are going to be the reactions? What will be this value? If this is 2 meter, this is 4 meter, what will be this value? I hope you remember the shortcut. If there is a point load on a simply supported beam, if this is A, this is B, this will be WB by L and this will be WA by L. So basically this is 1 times this distance, that is 4 divided by total, that is 6. And what about here? 1 times this distance divided by total, 1 by, okay, here also I'm going to get the same thing, which means 2 by 3 and 1 by 3. Here also 2 by 3 and 1 by 3. So I have all the reactions. Now I can use the table. So I'm first trying with the YC1 calculation. Okay, the Y, if enough space is available here, we'll continue with the YC2 here itself, or we'll use the next page. So I'm going with YC1. Okay, so segment 1. So I'm taking the section in segment 1. What will be the expression for bending? What will be the EI value? EI is EI. What about the origin? Decides whether I should leg to the left or right. In left I'm having just 1, right I am having a lot of forces, so definitely left. So left is point A, so I'm taking A as origin. If this is 0, what is the limit? Limit is 0 to 1 meter. What about the expression for moment? I'm taking the section here. On the left I'm having this force, and this, what will be the X here? X will be the distance from origin, which means this is my X. So RA1 times X is the moment, expression for moment. So what is RA1? We have the value, RA1 is 1. So 1 times X, and is it sagging or hogging? Okay, I'm taking the section. So section is here, load is like this, it is sagging. So what I have is plus 1 into X. That is the segment 1. What about segment 2? Segment 2, I'm taking the section in segment 2. So left or right? I prefer left. Okay, so I'm considering A as origin, EI. What will be the limit? This is 0, this is 1, this is 2. So segment is 1 to 2. And if you are thinking why I considered A as the origin, because I already have an expression considering A as origin. So you will find it easier if you are considering A as the origin itself rather than B. Let's see. If I'm taking a section here, what will be the distance x? Distance x is always taken from the origin. So distance will be taken from A. So my x will be this distance now. This distance is my x. So what about the moment due to Ra1? Ra1 times x, and it is a sagging moment, just like this, right? I have this, load is applied, it is sagging, and the magnitude is Ra1 times x. Ra1 is 1, which we have already got, so it's the same expression. That's why I kept the origin as A itself. So that's a contribution from Ra1. What about the contribution from this moment? Okay, so magnitude is 10, that's fine. What about the sign? Is it hawking or sagging? So now you have to use the concept that we earlier said. So this is a clockwise moment. So this is the point C. So I'm holding it in my hand. This is the moment clockwise. So apply. Okay, apply the clockwise. You can see that if I apply clockwise, it's a sagging moment, right? Clockwise moment is sagging. So it is plus 10. Okay, so that is done. Now the segment 3. What about segment 3? I haven't done this, I will come to that. What about segment 3? Segment 3, the section should be taken somewhere here. So better looking to the left, I'm looking to the right, because in the left I'm going to have one point load, moment and UDL. If I'm looking to the right, I'm having just one point load and a UDL. So I'm looking to the right, keeping point D as the origin. EI value is 2 EI. Okay. What about the limit? If this is origin, segment 3 is 0 to 4 meter. Okay. What about the expression? So what will be the x? X will be the distance from origin, which is this. Okay. Now, what about the moment? RD1 times x, which is sagging. So RD1 is 7. So 7x, then this part, that is minus 2x square by 2. This we have been using several lot of time. That's why I'm not explaining how we got this. UDL, leave around, you're going to get that. So we have the complete table for our YC1. Okay. Now these things are required. Let's try that also. These things are coming from the unit load figure. Okay. So I'm taking the segment 1. The segment 1 section is here. So I'm taking the section. What will be the moment? 2/3 of x. Right? These things are all same because I'm considering the small m figure of the same capital M. So these things won't change. Only these values we need to fill up. So the section 1 remains same. What is the moment there? 2/3 times x. Right? This is x. So 2/3 x. Now what about segment 2? If I take segment 2, it is again the same thing. 2/3 x. Okay, because the section is here and the left side what I have is just 2/3 and this is x, so 2/3 x. Now what about the third segment? Third section I'm taking here. What is the expression? 1/3 times x, because this is the origin, so this is distance x, so 1/3 of x. So I have the YC1, complete data of YC1. Now in this part, this is enough to write the YC2 expression, so let's write it here itself. So in YC2 I just need two segments, right? So segment 1, segment 2, and these are for YC2 values. Okay, so I'm considering segment 1. So I'll be taking a section in segment 1. Okay, and the section should be common to both the figures. Here also it should be common to both the figures. Okay, so what about here? Which side I should look, left or right? Left, because there's one. In right there are a lot of values. So I'm looking to the left. So when I look to the left, what will be the value? RA2 times x, right? This distance is x, so RA2 times x, it is sagging. So okay, let I write this. Here it is EI. Okay, what will be the limit if I'm taking A as the origin? the limit will be 0 to 2. What about the expression? We have seen that RA2 times X. What is RA2? RA2 is minus 2/3 of RC. So minus 2 by 3 RC times X. Now what about here? I need to take this section in segment 2. So which side is the preferred one? Left or right? I will prefer right because there is just one value. So this distance will be my X here. Okay. So what is the expression? RD2 times X. Okay, let's fill this first. The EI value is 2 EI. Then what about this? The limit, if this is 0, segment 2 is 0 to 4. Okay. And the origin I have taken as D. What is the expression? RD2 times X. What is RD2? It is minus RC by 3. So minus RC by 3 times X. So that's the expression for capital M. Now I'm considering here. What about here? What will be the expression in the unit load figure? Small m, 2 by 3x. Okay. What about here? Looking to the right, 1 by 3x. So that's the consolidated table for the YC1 and YC2 calculation. Now you feel that there are a lot of things in this figure how to solve it. Okay, you don't have to worry at all because here this answer you can directly get it from calculator. Okay, you don't have to write the long expression and you need to integrate it step by step because this is an integral with limits. We are having the limits, okay, and we have the expression. Directly you can put it in the calculator to get the solution. This one you may have to work out step by step. So let's try to solve it. Okay, so I'm keeping the paper apart and I know that I will require those for reference. So I come here and I'm going to do that. So let's see. I'm calculating the YC1 first. Okay, so I'm referring the previous sheet and I'm copying the values. So we know that what we want is, as per unit load method, delta is equal to integral mm dx by EI. That is the basic equation we are going to use. So YC1 is equal to integral. The first limit is 0 to 1. M times m, capital M times small m is going to give x into 2 by 3x, that is 2 by 3 x square. So 0 to 1, 2 by 3 x square dx by EI plus. The second is 1 to 2, okay, integral 1 to 2. What is the expression? 10 plus x times 2 by 3x, that is 10 plus x times 2 by 3 x dx by EI, because EI is EI. Now the third segment, the limit is 0 to 4. 0 to 4. Expression, when I multiply these two, and what I'm going to get is 2 cancels away. So 7x minus x square times x by 3. 7x minus x square times x by 3 dx, and you should be very careful, the value is 2EI. 2EI. So this expression is going to give me the value of YC1. So what I'm going to do is I'm going to feed this equation directly into the calculator because this is an integral with limit. There are no constant values. We can directly fetch the result using calculator. No need to go for the large expression. Even it is not a complex one if we are expanding it, but it is easy to use in calculator. So I'm going to use a calculator. And you should remember, you should take the 1 by EI outside before substituting it in calculator because EI is a constant. So this will be 1, and here it will be 1 by 2. Okay, so let's see. I'm going to substitute those values in calculator and let's see what I'm going to get. Okay, so on substitution in the calculator, I'll be getting the value as 26.11. That is YC1 equal to 26.11 by EI. Okay, I have the value of YC1. And the YC2 we need to calculate. So I'm going back, I'm again going to use the unit load method. So YC2 calculation. So expression remains same, integral mm dx by ei. Okay, so segment 1, 0 to 2 is the limit. Ei value is ei. Okay, we can do that. Now capital M times small m. So minus 2 by 3 times 2 by 3 rc x square. So it is basically minus 4 by 9 rc x square dx by ei plus second is 0 to 4 and whatever the expression rc by 3x, so it's going to be 1 by 3 times 1 by 3, that is 1 by 9 rc x square by 2 ei. Okay, always be very careful about the ei parameter. So I got this. Now I just need to integrate this. So this is not a hard part. Let's try that. So I'm taking the constants out. So in this the constants are minus 4 by 9 ei. Okay, it came out. And rc also I can take it outside because it's a constant. Now when I integrate is x square. X square becomes x cubed by 3 in the limit 0 to 2. That's the first part. What about the second? I'm taking the constants out. So rc by 18 ei. Okay. What left is x square. It becomes x cubed by 3 in the limit 0 to 4. So when I calculate that, what I'm going to get is x cube. So 2 cube divided by 3, that is 8 by 3 times 4 divided by 9. So I'm going to get it as minus 1.185 rc by ei minus the second one x cube, that is 4 cube divided by 3, okay, multiplied by 1 divided by 18. So what I'm going to get is again minus 1.185 rc by ei, right? Both are the same value. So when I calculate it, I'm going to get the final value as minus 2.37 by ei as my yc2. Now we have the values of yc1 and yc2. Now we can use the compatibility equation that we have already prepared, that is yc1 plus yc2 equal to 0. So I'm going to do that without wasting any further more time. So yc1 plus yc2 equal to 0, which implies 26.11 by ei plus minus 2.37 rc by ei, forgot to write rc here, equal to 0. So what will I get? rc is equal to, I'm taking this to the right side, so 26.11 divided by 2.37, what I'm going to get the value as 11.01 kilonewton. So that's the value of rc I'm getting. Okay, so we have the value of rc. Now what are the unknowns? rc we got, ra and rd. So if we have the value of rc, now this will be converted as a force, and it's the application of the concepts from engineering mechanics to get the solution. I will discuss it here because in the last lecture I left it for you. So let's try that. Okay, I'm plotting the beam. So what I have is ra, rd, and this is rc, which we got as 11.01 kilonewton. And then what are the other loads? There is a moment here which is 10 kilonewton meter, and there is a UDL 2 kilonewton per meter. Okay, so that's what we have. Now we are going to simply apply our equations of equilibrium to solve it. So first we are trying the equation sigma say md equal to 0. What will we get? sigma md equal to 0. What are the equations? There is Ra 1 meter, 1 meter and 4 meter. So total is 6 meter. So Ra times 6, right? Then what is there? Then there is moment, which is also clockwise, hence 10. Then the effect of this is 4 times this force, and it is clockwise, right? Clockwise. So plus 4 times 11.01. Then the UDL effect, that is minus 2 times 4 times 2. Okay, 2 into 4 is the force. Half of it, which is 2 meter from this point, is the lever arm, equal to 0. So from this, I am going to get the value of Ra. So I am going to get it as 2 times 4 times 2 minus 11.01 times 4 minus 10 divided by 6. The value what I am going to get is minus 6.4 kilonewton. Now what left is the value of Rd. For that I can use sigma Fy equal to 0. Considering upward as positive, I will be getting Ra plus Rd plus 11.01 minus the UDL 2 times 4. This need not to be considered when we are writing sigma F. So this equal to 0, which implies Rd is equal to 2 times 4 minus 11.01 minus Ra, that is minus 6.4. I'm going to get it as 3.39 kilonewton. Okay, so now I have all the values. Ra I got, Rd I got, Rc also I am having from the last page. So now all the unknown reactions has been solved. You can substitute this back in the figure and you can plot the BMD. So just for your reference, you are going to get your BMD. I will just plot it so you will get a feel of how it is.